Hello, Southwoods Math students. Mrs. Lindsay here to bring you part 2 of geometric sequence. How does the geometric sequence relate to the exponential function? If you recall a little review from yesterday, we have a geometric sequence here, and as you recall, you'll be given this geometric sequence explicit formula on your reference sheet. So really, all you need to do is identify the first term and the common ratio, and you can write the explicit formula. This sequence, 54, 18, 6, the first term is 54, and you would have to identify the common ratio. In this case, it's being divided by 3, but we always use multiplication. So we would have to say it's being multiplied by 1/3. The common ratio is always whatever you multiply to get to the next term in the sequence. So if I multiply 6 times 1/3, I get 2. 2 times 1/3, I would get 2/3. And the explicit formula would be 54, which is the first term, times 1/3, which is the common ratio, to the n minus 1 power. And again, because we're using the first term, not the y-intercept, we have to back it up one, so it's the n minus 1 power. The second example, we start with 1/2, so clearly that's our first term. And we're increasing, but not by a constant rate of change. We're multiplying by 4 to get to the next term in the sequence. So the next two terms would be 8 times 4, which would be 32, and 32 times 4, which would be 128. Again, the ratio is 4. The explicit formula would be the first term, 1/2, times the common ratio of 4 to the n minus 1 power, because we're using the first term and not the y-intercept. So on this next slide, we have arithmetic sequence. And in the arithmetic sequence, we're adding a common ratio. There is a constant rate of change. So 5 plus 4 gives you 9. And 9 plus 4 gives you 13. The next term would be 17, and so on. We could count until we get to 205 and then keep track of how many terms there are. Or we can use the arithmetic sequence explicit formula, which is again given to us on the reference sheet, to figure out what n is, because n is the number of terms. So if we know that a sub n is the term we want, the term we're going for, which is 205, and a sub 1 is 5, that's the first term, and d is the common difference, which is the constant rate of change, which is plus 4. All we need to do is write what we know into the explicit formula and use a little algebra to solve. We would distribute the 4, so we get 205 equals 5 plus 4n minus 4. Combine like terms. So again, we'd have 205 equals 1 plus 4n. We'd subtract 1 from both sides. That would give us 204 equals 4n. And we'd divide both sides by 4, which would give us 51 equals n. So there would be 51 terms in the sequence. So knowing most of the formula, we can solve best. You can see the answers on the next slide when you go through your slides on your own. On the next slide, we're given a sequence 6, 18, 54, and we're asked to use the geometric sequence explicit formula. And in this case, I'm giving you a chart or a table. And the table many times is the best way to figure out your function form or even your explicit form. Now the explicit form, again, there's no need for the calculator. All we need to know is the first term and the common ratio, and we can copy it off the formula. So since the first term is 6 and the common ratio is 3, we're multiplying by 3 to get to the next term. That's times or to the n minus 1. So each of these is being multiplied by 3. So if we want to create a table, which we've done, and type this into the stat menu on the calculator, the stat edit, and then the stat calc, you'll find it number 10, the exponential regression, we're going to be given something slightly different. We're going to be given A and B. Instead of the first term, we're going to actually be given the y-intercept. So if the y-intercept is A, which is 2, and B is the common ratio, which is 3, which is the same as the common ratio in the explicit form, and that would be raised to the x power. So these look slightly different, but if you type these into the y equals in your calculator, both of them, you'll find you get the exact same function. The only difference is with the geometric sequence is what we call discrete. So the geometric sequence, this 6 times 3 to the n minus 1, would be just these dots. But they would look just like an exponential function. They wouldn't line up in a straight line. They would be a curve, like an exponential function. But they would actually be the same pattern. They look different because the explicit form of the geometric sequence uses the first term, and the function form of the exponential function uses the y-intercept. But they are exactly the same, and you can prove that with the calculator. So here we have Davia and Miguel talking about two functions that look different, but are actually the same function. So in this case, Davia is using the explicit geometric sequence form. And Miguel is using the expo, the exponential function. If you type these into the y1 and y2 in your calculator, you'll find that the table is exactly the same. Okay? So these are exactly the same function. If you graph them on your calculator, they are exactly the same curve. The only difference is the geometric sequence would be the dots, discrete. To prove they're the same function, type them into your calculator and check out the tables. All right? If you look at the graph, I typed them on Desmos, they both are exactly the same graph. So for your turn, you're going to try with this is supposed to be a arithmetic sequence, sorry. Use the arithmetic sequence to find how many terms, so you're going to find n. You can use algebra, or I guess you can just count up all the way up to 55 and see how many terms are in the sequence. Algebra would probably be the best way to do it. You know A1, you know D, you can find N. And on the next slide, you can look at two different functions, right? The explicit geometric sequence and the exponential function, and see which one matches. So good luck. Any questions? Give me a call. See you online.